Now let us identify f theta from 9 and 7, from 7 and 9. So scattering amplitude f theta can be identified as sum over L, Al, I to the power L, e to the power minus I del L divided by twice Ik into minus 1 to the power L SL minus 1 PL cos theta. So now if we put the value of AL in this expression, we have AL as I to the power L twice L plus 1 e to the power I delta L. This is the expression for L. Now substitute this L here. We get I to the power L twice L plus 1 e to the power I del L. This is for L. Then we can write I to the power L e to the power minus I del L whole divided by twice Ik into minus 1 to the power L SL minus 1 PL cos theta. Now looking into this expression, it reduces to sum over L, the FL PL cos theta is the most vital expression. Let it be expression number 11 because here was expression number 10, this is 11. The term FL, which we call the Lth order partial wave amplitude. Lth order partial wave amplitude, which is from this relation we can write it easily as twice L plus 1 by twice Ik SL minus 1. This part is called the nth order partial wave amplitude. So look at this expression 11, that the scattering amplitude f theta can now be viewed as a sum of partial wave amplitudes. And this is the beauty of this approach, where we can visualize the scattering phenomena into many parts. Depending on the parts are classified in terms of the angular momentum L values. Right. Now let us write it once again in full form. It will look like twice L plus 1 by twice IK SL. SL means e to the power twice I del L minus 1. Again it can be written in this form, twice L plus 1 by K into e to the power I del L into sine del L. It is easy to follow that if you take common, if you take common e to the power I del L from this bracket, so we will have a relation of e to the power I del L minus e to the power minus I del L, so that will reduce us to sine delta L. So this is the expression for your partial wave amplitudes. Let it be noted by expression 12. Most important of this derivation and is that the f theta is now related to as an infinite series summation over partial wave amplitudes, right? We know the differential cross section d sigma d omega is nothing but the square modulus of f theta. So we have to put here the values of f theta to express this d sigma d omega in full form. So let us do that. Recalling the expression for f theta, we can write in this way that 1 over k square sum over L. Since it's a square, so we have to take two summation into twice L plus 1 for one type of L and twice L prime plus 1 for the other type of L into, say it is e to the power I del L e to the power minus I del L. Then there is also one term like sine delta L prime into PL cos theta into PL prime cosine theta. One thing we can note here that this expression is number 13, that as there are terms for L and L prime, it gives an interference. It is interference terms corresponding to, it gives interference corresponding to different values of L. Now the total cross section sigma can be written as twice pi 0 to pi d sigma d omega sin theta d theta. Okay? Now if we put the values of d sigma d omega from this last expression, say 13, then quite naturally we will come across with such a situation where this PL cos theta and PL prime cos theta and this sin theta part will be involved in the integration, and for this point we need the orthogonality relation. The orthogonality relation of Legendre polynomial is your this much 0 to pi PL cos theta, PL prime cos theta, sin theta d theta is your 2 by twice L plus 1 delta L prime. Okay? Now this relation tells us that when L prime are equal, then only this relation gives us a definite value. So, considering that situation, we can rewrite the expression for total cross section in this way: sigma equal to 4 pi by k square sum over twice L plus 1 sin square. Again, this total cross section can be written as sum over L sigma L. Just like your FL, here the total sigma is a sum of infinite number of small sigmas, and those sigmas are known as partial wave total cross section. So, say this is the expression for 14, and sigma L is known as Lth partial wave cross section. Here also we can comment in this way that corresponding to a particular L value, the sigma L will be maximum only when this delta L become odd multiple of pi by 2. That is what I like to say, that sigma L max sigma L max equal to 4 pi by k square twice L plus 1, when the change of phase delta L becomes odd multiple of pi by 2. Right? Is it clear to you all? Question 16. We like to say about the node, points to node. So points to node. One, if we look back to the expression for differential cross section, I mean d sigma d omega, you look, this expression contains a physical facts of interference. Why? Now this term, this expression, it contains superposition of different partial waves. And which in turn gives us the interference effect. Interference effect in differential cross section. And it is also interesting to note that when we pass over from this differential cross section to total cross section, by integrating this factor over sin theta d theta d phi, we arrive in such a situation that this interference effect goes over in total cross section. In total cross section sigma, while integrating d sigma d omega d theta, while integrating d sigma d omega over d theta. So, in differential cross section, there is some interference effect. But in total cross section, that interference effect goes over. Now, we shall pass over to next interesting point. We would like to discuss here is the connection between forward angle scattering amplitude that is f theta equal to 0 to your total cross section sigma. Let us see what is it actually. We may recall that the scattering amplitude f theta can be written as 1 by k sum over twice L plus 1 e to the power I del L sin delta L into PL cos theta. This equation we already have derived for the point 2. In the forward direction, that is when theta equal to 0, we get Legendre polynomial PL cos theta as 1. Therefore, then f of theta equal to 0 can be written as twice L plus 1 e to the power I del L sin delta L. Now let us consider from this equation the imaginary part of f theta equal to 0, that is a forward angle scattering amplitude, which can be written as 1 by k sum over L twice L plus 1. From this e to the power I delta L, when we express it in cos theta sin theta, then it will become as sin square delta L. Therefore, if we multiply it by 4 pi by k, so 4 pi by k imaginary part of the forward scattering amplitude becomes 4 pi by k square sum over L twice L plus 1 sin square delta L, which is equal to the total cross section sigma. Now let us call this equation as equation 17 and mark this equation by 18. Now this expression, I mean the equation 18, is known as optical theorem. So in scattering of light, same relation comes as the interrelation between absorption coefficient and the imaginary part of the complex refractive index. So in case of optical phenomena where scattering of light is discussed, there is a relation in between the absorption coefficient and the corresponding imaginary part of the complex refractive index. And so, while writing this expression, we call this expression as optical theorem. Okay? Now, still we can discuss a few lines more. Well, my student, we all know that in arriving at this equation, at the beginning, we started with a system of elastic type of collision. Now, so we may think that optical theorem is valid for elastic case only. You should keep in mind or wanting to note that this relation is also found to valid in inelastic collision too. What I like to say? That the optical theorem, which is the relation of this type, the total cross section is represented or equal to 4 pi by k times the imaginary part of the forward scattering amplitude. This optical theorem is valid not only in elastic case only, it is valid both for elastic and inelastic collision. So we can say that the optical theorem is a general feature. Is a general feature of scattering phenomena. Whether it is elastic or inelastic, no matter, the optical theorem is valid. Now we arrive at the end point of our discussion under part 2.